Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 83, I chat with Philip Clements about his HPass speaker loading technology. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, recorded October 17th, 2011. Episode 83, How Low Can You Go? This episode of Home Theater Geeks is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Hey there, Scott Wilkinson here, online editor of HomeTheater.com. This week's guest geek is Philip Clements, the president of Solus Clements Loudspeakers and the inventor of a really cool speaker technology called HPass. Philip, hey, how you doing? Welcome to the show.
Very well. Good to see you again, Scott.
Yes, and you. Those who are tuned into the chat room at irc.twit.tv or watching live at live.twit.tv can post questions for Philip. I'm watching the chat room here as we go, and I'll pass on as many as I can. So, Philip, I wanted to have you on the show for a long time because of this technology that you invented, or at least refined from a much earlier and less sophisticated type of base loading. You call it HPass, which stands for?
It stands for Hybrid Pressure Acceleration System in this case.
Okay.
I actually did invent this almost 30 years ago, actually, a little over 30 years. Back then, of course, unfortunately there were no teal small parameters and no computers and no software. If you really enjoyed speaker design or wanted to be involved in it, there was even very little knowledge base and one hard to find to really try and figure out what you had to do. It was an awful lot of cut and paste. There was an awful lot of developing your own formulas back then. And
so it was almost as much of an art as a science at that point, eh?
It was, yeah. Well, we used to call it a kind of a voodoo science back then, to tell you the truth. So but nevertheless, there were lots of good things that did come out, and ultimately, with computers and so forth, that saved the day for an awful lot of the science, which caught up very quickly. And it was a couple of years ago when I had a chance to put this technology to the test on today's modern equipment, and that's when I realized that I could do some really fine things in smaller cabinets with smaller drivers and achieve even lower responses with more dynamics at the same or greater amplitudes, and that's what I've done.
Now, I understand when you say that you have invented this, and it really is a departure from anything else that's been on the market up to now, but wouldn't you say that it is at least an evolution, a step beyond bass reflex speakers?
By quite a margin, yes. The reason we call it a hybrid is because there are the attributes of 4 different types of bass loading involved in the design of this speaker. Definitely bass reflex is one of them. You have a vent, and to most people a vented speaker means a bass reflex design. Of course, that can also be a transmission line speaker that a lot of people have come to enjoy and know today. A little more complex, a little longer labyrinth type of a line involved in it, a little different type of science to it. But nevertheless, a vented speaker, and the reflex, of course, has been around a long time, and does have a lot of good attributes, but there's some weaknesses as well. HPass includes also, because there's a back pressure in the line involved in it, even a sealed speaker attribute where you would get something consistent or a little more so even with acoustic suspension type of drivers. So right away you have a vented system which will have your dual peaks that your transmission lines will have and your bass reflexes will have. You'll have the same type of thing. You'll have obviously a second output, which is the port itself. In sealed systems, you'll even have a backup due to the line source itself. We have pressure on the back of the woofer cone. That is taken into account and balanced internally in the cabinet, like you would the same with a sealed system. And in part, because of the way it does it, it acts like an inverted horn, and it does tend to follow horn theory. So what we have is about 4 different types of speaker base loading, if you will, that are included due to the attributes of the whole system when it comes together.
Let's briefly go over those 4 technologies and make sure everybody understands them. Bass reflex, or a vented speaker, is a speaker box in which there's simply a port or an opening in the box, which is otherwise just an open box. Is that correct?
That's correct, as opposed to a sealed box where the woofer itself would just fit into the box, all the rest of the box is sealed. So there's no other type of external opening to the outside area environment. In a reflex, you will typically have 1, sometimes multiple ports, even where there's more air coming out as well from those besides the woofer, which is moving its own air.
Now, what are the classic advantages of the sealed box or acoustic suspension design versus the ported or vented box or bass reflex design? Again, I'm talking historically now, not HPAS in particular. We'll get back to that in a sec.
Yeah. Well, the sealed boxes, if they're properly designed in the days of the OKLH and Advents and those types of products, if properly designed with the proper back pressure involved against the cone, you could extend the response, and of course you simplify the box itself, not having to have a second hole, not having to have an extra port or a tube. So there's simplification. There are some folks as well that like that type of design for its time element, where there's no delay basically from the woofer response to that of the mid-range or the tweeter. So there are some good things about it. The problem was it used to be less sensitive, and when you go to porting a speaker, a proper design, you can gain either the same extension of range with greater sensitivity, or you can go to an extended range with the same sensitivity, and you can go to even a smaller box and get the same extended range as if it was a sealed box. So the vented box made a lot of differences. Its disadvantage is that you're unloading the woofer basically itself, and that allows it to be a little more loose and a little more floppy inside in the cabinet itself.
Which means I think that its response, particularly to the beginnings of sounds, the transients, is less well defined.
That's correct, and because of that, you can get, certainly if it's not tuned properly, you can get a much more of a boomy sound, or you can even get a shallow sound if it's tuned too low, because you will lose output as well from the vent itself. You won't have a smooth response in the transition from the vent to that of the woofer again. But that looseness in the woofer can create extra distortions also.
And then we have what's called transmission line, which is basically a tube placed behind the woofer and directing its sound along a particularly shaped tube on its way to the vent in the box, as opposed to simply a hole in the box.
That's correct. And because of the length of the line, this somewhat of a labyrinth, if you will, you can get a lot of resistance, and that's why a great many of the transmission line speakers, the old IMF Freeds, and many of the older designs were quite inefficient, very insensitive, even down in the 70s, and you needed Dallas Power and Light, if you will, or Con Edison to drive the things with. But they did have a tremendous extension of range, most of which is based on what they call quarter wave theory, where if they can design the length of the line to be a quarter of the wavelength of the frequency to which they're wanting to derive in terms of that which exits the vent, you would have to have a length in that whole line that would be a quarter of that wavelength. So if you wanted to tune to 40 hertz, then you'd have to have a line that would be long enough to be able to do 1/4 of that or a quarter of that. So that's where the transmission line influences come from. Still probably the least amount of that particular technology known of all the different types that are out there today.
We got a question in the chat room that skipped by me here. Big Don asks, how does magnet size figure into your particular type of speaker?
Same way it would in any other. I mean, magnets by themselves don't necessarily change anything. It's a question of whether or not most of the time it's considered to be a larger magnet, therefore you're going to have more output in most instances, but that depends on the size of the gap and how much area the voice coil is sitting inside the gap. If that gap is fairly large, even with a larger magnet, you really won't get any additional output. So in going to larger magnets, however, and especially in this case and in today's many speakers, deeper magnets, what that does allow, assuming the same sensitivity all the way around, same size gap and everything, what that can allow, if properly designed, is greater throw, what they call a longer throw, which you see in a lot of today's subwoofers and even in some of the normal 8-inch, 10-inch, 6-inch type of drivers today, in order to try to get a little lower response and a little more linearity over a broader range.
Mm-hmm. But HPAS takes care of that in a different way, right?
Yeah, absolutely. One of the parameters that we still like to have is a fair amount of what they call X max, which is the distance that the moving mass can throw and still stay within the gap properly. And that X max is for major transients, where you would have something that would hit like a bass drum, and you would get a quick, big transients, which would require the woofer to throw a specific distance. What you do want, though, along with that, unlike most woofers which have a very low resonance to try to achieve that in fairly large boxes, you want it to recover extremely quickly so that you get the benefit of that quick transients and then a stop. And that's where HPAS comes in.
Mm-hmm. BF3 in the chat room says that he built some speakers with reflex bass. Sounded like bass from a room next door. Awful. Now, that I think speaks more to the knowledge with which anyone trying to build their own speaker brings to the table. It's really not a simple task to design and build a speaker.
Well, I can certainly empathize with him. I can assure you, Scott. I've built a few of those myself. But there's no question about it. There is a science to it, and in the days when it was a voodoo science, it was really a hit and miss. And I'm not sure any of them back in those days were dead on. Some of them were pretty good and probably pretty close, but there weren't a lot that were what I would call as well tuned as you can get today. And there's lots, if you're involved in speaker design today, there's lots of places online where they have all of the computer information. You can even use the algorithms and things that they have online to plug right in some simple stuff and come up with some pretty darn good alignments for your bass.
Mm-hmm. Web4655 asks, what about waveguide speaker technology? I think waveguide's just another name for transmission line, isn't it?
In part, I believe so. There's a lot of I think, ways you can apply the term waveguide. But I do believe that it is more involved with, again, as a transmission line, a specific length of the line required to achieve a certain amount of wave, quarter wave, eighth wave, whatever it might be, in order to get to tuning point that you would need. And so you would need a certain distance in that particular line. The waveguide in this instance is usually, though, mostly the same, in most instances that I've seen it, is the same diameter pretty much through the entire guide itself, as if a long port, if you will, and there can be some variations in that.
I've also heard the term waveguide applied to horn speakers, and the horn itself being called a waveguide. Have you heard that?
Well, that's what I was suggesting, is that there's lots of ways to apply that.
Yeah, because that's in front of the driver rather than behind the driver.
That's correct, and there are some, even though, that do have off of the back wave of the drivers. I've actually seen speakers that also use that information in the form of a horn, typically a standard horn, which can be either a conical or an exponential of some type, and use that back wave information. But Bose obviously has done a phenomenal job with what we think today of typical waveguides, which is what we were talking about, I think, a little earlier.
Now, we've got a picture of the internal workings, the internal structure, I should say, of a couple of your speakers that use this HPass technology, which is a hybrid of the at least the three that we were talking about: acoustic suspension, bass reflex, and transmission line. I've forgotten what the fourth one was. You said there were four.
A horn. Kind of a horn.
Right, a horn.
Yeah.
Kind of a horn.
In this case, an inverse horn, yes.
Right. And that would be, there were two pictures that I sent up to John that are the Solus 6, the first one that I sent, and then the Solus 4, which if we can show would be good. I'm having a little trouble with my video coming back. I hope it's not. Well,
the one I see right now is the tower, which we call the 6.5T for the lack of something better right now. And all of these products are due out to be available in January sometime. But let's take a look at the tower here, which I see up here right now.
Yeah, I got it.
Okay, you'll see the front, which shows the cutouts for the woofer and the tweeter there as a two-way. It is a 6.5-inch woofer. But let's take a look internally, if you'd like. And you can see that right behind the woofer, effectively, there is an area internally inside the cabinet. You see a couple of braces, so to speak, going across the cabinet. Those are just internal braces. If you're looking at in color, the kind of purplish item in the back is the crossover board. That's where the crossover would be mounted, if you will. Okay. And then the cutout right below it is the terminal cup where the terminals will be mounted and connect to the crossover. Now, right underneath the woofer is the first structure that becomes real important internally, as you can see, done in somewhat of a red or orange red, where it protrudes from the bottom of the woofer cutout somewhat back into the cabinet. And at the end of the first one, you can actually see an intersection. We call that horn plate 1, actually. And you can see what it's done is that because of that protrusion back into the cabinet, it's actually cut the cross-sectional airspace off by what might be 3 or 4 inches of internal depth, so that we have now compressed, if you will, some of this air wave that is coming off of the back of the cone as it starts proceeding down this particular line. I don't see it anymore right now. I don't know where it went. It was still there? Okay, there we go.
Yeah.
And okay, that's horn plate 1. If you could kind of move it up. Yeah, there you go. Back out. Just there we go. Then you get to horn plate 2. Well, if you'll notice horn plate 2, that it's attached to 1, it actually has a different rate of the way that it closes down as it continues closing and continues to cut off the airspace, if you will, that's left inside the cabinet. So effectively here, what you have right away are 2 different rates of taper that are closing this thing down. and there's two different lengths as well here, and we still haven't gotten all the way. Horn theory tells us the longer, the tighter the taper rate, the lower the cutoff frequency. So you're dealing with both the length of the line and you're dealing with the taper rate in order to achieve either openness for standard horns or a tightness, in this case, to achieve compression. And that compression backs the information up against the woofer cone, which is what I was talking about earlier. As we get to the bottom of horn plate 2, if you'd like me to continue on the cabinet.
Yeah, sure.
There's an opening all of a sudden that goes into an area between the front of the speaker and the horn plate itself. That particular area I have always referred to as the acoustic bass trap. What it is just an area that has an opening in it, just like a bottle that is opened on the top, and is effectively a typical Helmholtz resonator. The key here is the size of the trap in terms of how large a wavelength that will allow into it internally. And should you then take and put damping material in there, you can take that specific wavelength and others that are related to it, specifically higher ones in particular, because bigger ones you can't get in there, and you can reduce their amplitude, because what happens is that obviously as the air goes in and goes through damping material, creates friction. Friction creates the heat, and then energy is lost as heat before that air starts to reappear coming out of that particular area, just like blowing over a Coke bottle, if you will. And if you do it at a certain degree of pressure, it will then push that air right back out and create a tone. That air then comes back into what becomes that compression line down to that point, proceeds to the bottom of the cabinet, and at the bottom of the cabinet you can see some blue, what looks like some blue items. And what those are effectively horn. The bottom red one is horn plate 3 that extends back from the front of the cabinet to the back where the opening is in the line. But those two blue items you see there are continuing compression plates, if you will, from the back of the speaker now to the front. So it takes the general width that is right in the back of the speaker at that point, being compressed down to that point already, and continues compressing it all the way to the front of the speaker where you see the exit from the vent.
So the vent is in the front of the speaker.
That's correct. It's in the front of the speaker. So all that back wave has gone now down through these 3 horn plate sections. It's actually gone into and out of the trap area, back out of the trap, and then through the bottom section of compression and then out into the room. So that's the general airflow in the cabinet.
F-Loop in the chat room asks, Atlantic Technology is claiming that 2 5-inch woofers with 4 millimeter X-Max can do 30 hertz at 105 dB when loaded with HPAS. Are these claims realistic?
I can assure you they are, because I did the bass bottom for that product. That was the one. Peter Tribeman is a great friend and long-term friend, and it was Peter that asked me. And
he, by the way, is the president of Atlantic Technology.
That's correct. Yes, and he's the one. As we were right next to each other at one of the CES shows, and he said, "Phil, I need a tower to go overseas." But I want something different. And I remembered that old bass you used to have. Why don't you take a look at it again for me? And I wasn't even sure I wanted to open that can of worms again, to tell you the truth. But he talked me into it, the silver-tongued devil that he is. And
yes, he is that.
And that's when I pulled it out, and I recognized there's something here we can really do, because the first iterations of what we have today were obviously crude, but worked well and was patented then in full for 17 years. But this would bring it a long ways forward and up to date. And that's what we did. And, of course, we've applied for patents again. But in doing that particular product, the base section of that, those drivers are about 88 to 89 dB sensitive. Together, they're 8 ohm drivers that are parallel as 4 ohms, and the internal size of the cabinet I think it's a little over a foot and a half cubic feet. I could be wrong. I don't remember just offhand because we did that about a year and a half ago. But the response curves on that were almost flat to 32, 33 hertz. And then the roll off on it was a 3 dB down was about 29 to 30 hertz in that range. But the key for the sensitivity is the pressurization. 99% of all speakers out there today do not have an even sensitivity. They're all rated, for example, at 90 dB, 1 meter, 1 watt, whatever the rating may be. But that's typically either an average over the whole speaker or a limited range or one frequency like 1,000 hertz. Effectively, as you go down in response, especially below 80 hertz, you start losing sensitivity big time because you're up against impedance curves and a lot of other physics that start draining power, and consequently you start needing more power. The sensitivity is going down. That's why. That's why only a fully horn-loaded system down to its cutoff would have the same sensitivity. Because of the pressurization in HPAS, you actually have a greater or equal sensitivity from 80 hertz down as you do the rest of the system. And that's why we not only get the range, we get the dynamics and the output that that the woofers are capable of themselves up to their point of no return.
Right. F-Loop's continuing question is, does this mean that the speaker can achieve 105 dB at all bass frequencies above 30 hertz? And I think what you just said implies that it can.
That's exactly right. You want a smooth response, and I even sent a couple of response curves to you that we might get a chance to look at later. But that's the whole idea, is to obviously have a smooth response. You don't want to have holes. You don't want to have a big peak in it. And because of the way HPAS works, you don't get the big one-note peaked responses if properly done. And you get a very tight, clean, extended sound, and you can definitely hear the difference. There's no doubt about it.
Now, let's see if we can get the photo or the diagram of the frequency response of the Solus 6.5. There it is.
There you go.
So explain to us what we're looking at here. This is the first of two that we're going to be looking at.
Okay, well, this one here is actually 3 different curves. These are the ones I like to run. You'll see, first of all, one in red. And this, by the way, is set up from 10 hertz out to 300, just showing the low end. The one in red is basically the woofer measured near field in the cabinet, showing its typical roll-off, if you will. And the blue curve is the vent taken near field as well, with the microphone right at the vent. So you can see what the output is like at that vent. And note on that a couple of things. One, that the output of that vent at its peak through that 30 to 40 hertz range has more output by 2 to 3 dB or more than the maximum amplitude of the woofer around 250 hertz. This does not happen with typical bass reflex systems. If you've seen the curves of the vent in most of them, the amplitude of the vents is actually below that of the highest amplitudes of the woofer itself, and usually have a much broader output on the high end, which then interferes with the woofer and gives you that one-note boomy bass because you get a peak in the response. The purple curve below that is the summed curve, which is a far field curve taken of the other two that are averaged through the computer. And as you can see, that's a pretty flat curve. There's probably less than plus or minus a half a dB, all the way from about 35 hertz, which is right where you see it starting to roll off, somewhere around 35, 36 hertz, all the way out to 300. I sent another one out to 500 showing how flat that particular one happens to be.
Right,
but,
that was the second graph with having to do with Solus. There it is.
There you go. There you go. That one does show all the way out to 500, and once again, you can see the yellow line at about 36 hertz there, if it's viewable. Right where it starts to roll off, and from there on down, if you can count your 3 dB, you're right about 30, 31 hertz at the minus 3 dB down point. And you can see each one of those divisions, by the way, those lines is 1 dB. So that's a pretty that's a pretty flat response. You're not going to see that kind of response through that frequency range very often. Now that happens to be my product, but Peter's product of the AT1 with the dual 5 1/4s, I use a 1 6 1/2 in mine, has the same kind of response, and his actually goes a touch, maybe a touch lower, or maybe a 1 or 2 cycles. I set mine up to provide as much of an output. You can do it both ways, but it's so close you can't really hear the difference. So I'm always an output guy if I can be that, as long as I've got the range I want. So that was that's the way they look. Can we go back to that one graph that had the had the 3 lines? That had the blue, the red?
Sure we can. I'm sure we can. There it is.
I wanted to point something out on that. If you look at the blue graph, which is the vent, you'll notice that it doesn't start rolling off. And first of all, the amplitude's up between 30 and 40. Right. And it doesn't start rolling off till you get to about 31 to 32 hertz. I mean, the output is pretty flat out to that point. And then if you start counting down 2, 3 dB, you're right around 29, 28, somewhere up in there. But what's important, when you come down that 2 or 3 dB, the amplitude at that frequency coming from the vent, in other words, the output, which in this case measured at the vent is about 100 and, well, at 32, it's about 117 dB or so, 118 dB or so. At 3 dB down, we're about at 115. That is at 29 hertz, and that amplitude is identical to that of the highest amplitude of the woofer itself at 250 hertz. Now we're talking about something very different than a typical bass reflex or a transmission line in that respect. Now we have a sensitivity that's equal to or greater than, and through the 30 to 40 hertz range, it's greater than that of the woofer itself.
It's amazing. It's amazing. We were talking a little earlier about impedance, and there was a question a little while ago in the chat room about whether these speakers are 4 or 8 ohm nominal impedance. And you can answer that question while we pull up the graph of the impedance curve, which, as you pointed out earlier, is not the impedance is not constant over frequencies.
Oh, absolutely not. And there's very few speakers that are done that way, and certainly if they are, they're very much designed that way. And it can be good or bad. No one thing makes something that much better or worse than something else in terms of one specific parameter of any type. It's all a synergistic effect with every speaker. But if you look at the impedance curve on it, a couple of things. First of all, the impedance typically is defined by the impedance of the driver. In the case of the 6 1/2 inch, this is a 6 ohm driver. So if you take a look at if we take a look at this, again, this response is from 10 hertz out to 20K. So this is the entire system in this instance. The first thing to look at is the saddle, which is what the lowest impedance point is between the 2 impedance peaks to the left of the graph. That particular point is typically the tuning point of the vent itself. That's where we're tuned to. And as you can see, it's right on. It's right at 35, 36 hertz. So that's and that's right down to where the speaker goes to. It can be, the pressurization in the system can be applied such that while you can tune to 35 or 36, you can actually get extended range on down another 4 or 5 cycles below that. In this case, I didn't need to because the line was long enough already to get where I wanted to go. If you move over to around 100 and, what might be 220 cycles or so, somewhere right in there, that's the lowest impedance point in the entire impedance curve of the speaker itself, which is right around 5.6 to 6 ohms, somewhere in that range. And as you can see, if you went from 80 hertz, for example, all the way out to 20,000 hertz, because there's very little variation in the impedance curve, probably less than about 3 ohms. Now, that means that the lowest impedance point being 5 1/2 to 6 ohms, and a variation of no more, the worst up from 80 out being maybe 12 ohms, you're looking at plus or minus about 3 ohms. That's an extremely easy load to drive, meaning even amplifiers that may not have the best power supplies, receivers of all types, which can have some good power supplies, but any receiver, any type of amplifier would be capable of driving this speaker.
Exactly, which is really quite good, and something I'd like to make sure people understand, that when you go shopping for a speaker and it says they're 8 ohm or 4 ohm, that's only what they call nominal impedance, and the impedance actually changes quite a bit over, or can change quite a bit over, the frequency spectrum that the speaker is reproducing. And what you're saying is that yours changes less, and it doesn't go as low as some.
That you can get into lowering that. Some people design in 3 ohm speakers, sometimes less. It depends on the crossover type you might use and how it is also designed into the system. Typically, you'll get much higher peaks if you use steep slope filters like 12, 18s, and 24s. I tend to like 6s on the bottom ends and maybe 12s on the high end, although I have done things at 18s as well. But I do.
By the way, those numbers refer to the number of dB per octave that the crossovers are filtering one set of frequencies from another. And the steeper, that really refers to the steepness of the cutoff between one frequency range and another. And the steeper it is, generally speaking, wouldn't you agree, the more problems you have with things like phase response and that sort of thing?
Well, that is the biggest problem. And again, there's always give and take in speaker design. The advantage is that if you cut it off more steeply, you should get something pretty clean. Secondly, not all speakers, the drivers, are as linear as people would like to have. And so a lot of times you need a steep slope filter to maybe cut out some part of the curve or make it behave in a way that you want it to, so it doesn't interfere with some other part of the response. To have an open slope or a 6 dB, you have to have pretty darn linear, very smooth drivers in order to be able to make that work properly. I do something in my designs that I've not really seen other people do. I do like 6 dB per octave on the low end, mostly because of the lack of phase shift. But what I tend to do is design my woofers to go out to a certain frequency range on their own, roll off at about 12 dB per octave then on their own, such that when I add an impedance compensation network, or if you will, a Zobel, then what you get is you add the 6 dB to the 12, and you get an 18 dB per octave roll off, and then you can use the Zobel to fine tune the roll off rate a little bit and exactly where it occurs. And that provides then the opportunity to get a very clean, quick, steep slope, but you do it with a very open electrical filter and the lack of phase shift. And the impedance network helps with that as well. So with that, you get a broader, bigger, more open, uncompressed sound, which is why I like those.
Okay, very good. We got another couple of questions in the chat room that I'm going to get to in a moment. I hope you'll pardon me for just a second while I thank our sponsor for this episode, which is, of course, Netflix. Now, those of you who are watching the show and listening to the show probably already have Netflix, so I'm preaching to the choir here, but nevertheless, it's important to spread the word, I think, because Netflix streams thousands of TV shows and movies instantly and directly to you, which means you save time, money, and hassle over physical discs. You can, of course, also get physical discs, but I've really been getting into streaming lately. It's so convenient that it just satisfies so many desires for wanting immediate gratification. There are several easy and instantly accessible ways to get your content from Netflix. You can watch movies and TV shows on your Mac or PC, of course, or your iPad or the iPhone. Anywhere you are, you can catch these things. You can also get it on most TVs and Blu-ray players. So just about any device you have these days is going to have it. You can get it on your gaming console, Xbox 360, PS3, or Nintendo Wii. If you're not a gamer, which I'm not, you can get it on your TV with Apple TV or a Roku box. which are all very inexpensive and easy to use. With Netflix, you can watch movies and TV shows instantly using any of these devices, and you can even begin watching on one device and finish watching on a different one. Whichever way you choose to access Netflix, you can watch as many movies and TV shows as you want, anytime you want, and you can cancel anytime. We're actually offering, Netflix is offering a free 30-day trial for Twit listeners. Just go to netflix.com/twit and be sure to use this URL when you sign up for your free trial, netflix.com/twit. And we certainly thank Netflix for their support of the Twit network. Okay, so in the chat room, F-Loop asks, did modern simulation technologies make HPAS possible, avoiding the trial and error you talked about earlier? And when did simulation finally catch up with the voodoo art, as you called it earlier?
Well, the catching up time frame was the beginning of the 80s when Mr. A.N. Thiel and Mr. Small developed what we know today as the Thiel-Small parameters, which were characteristics of every particular driver, where they talk about the Q, the total Q, the electrical Qs, and so many different things involved with the driver. There's probably a list of maybe 15, even 20 different parameters that computer analysis will provide and help do today because of what they've done, the software that the things they identified then and the software they wrote to go with that. The technology itself did not require that we had that available. But as mentioned earlier, because I did that 30 years ago, that was a lot of trial and error. I had a 10,000 square foot warehouse at the time, and about 9,800 square feet were filled with prototypes back then. So it was definitely trial and error date, particularly dealing with something that sounds somewhat complex. It's not as much as now that you understand it more, but back then seemed somewhat complex. But there's no doubt that the computer era has aided without fail the ability to optimize this technology. Without that, it would have it may have taken another 100 years to try to optimize it.
Virgil in the chat room asks, is the placement of your speaker different than other speakers? Do you have different placement suggestions for these?
Not really. I think that depends on the room an awful lot more than, in this case, the speaker. Being front-vented, you don't have to worry about, and being, it's not bipolar, so being a monopole-type speaker and front-vented, you don't have to worry too much about placement. Obviously, as you get back closer to walls, you're going to pick up more bass reinforcement just due to the walls. How close can you get and how far away? That depends maybe on how wide the wall is before the first intersecting walls to the back wall, where you'll begin to get that reinforcement. How high is the ceiling? How much cubic footage is in the whole room? Is the room fully enclosed, or is there a complete wall that's totally open to another part of the house? So I always try to suggest that the best thing you can do is to do a little playing with that, and wherever it suits the needs for the best sound, and what the lady of the house will allow.
Well, there is always the spousal acceptance factor.
Yeah, we call it the wife factor, or the WAF, if you will.
The WAF, yes, exactly. I've been getting some comments in the chat room that bass reflex, which this isn't, partly, I suppose, but not really, doesn't sound natural. And BF3 here says, my idea of a great speaker is a studio monitor. And that commercial speakers with bass reflex you will never see in a studio. Which brings up the question that I often ask speaker designers and audiophiles, which is, studio monitors are intended to be quite flat, whereas consumer speakers are often tuned such that they aren't entirely flat. Now, your speakers, as we saw earlier, have a frequency response that's ruler flat. And how do you feel about that as opposed to many consumer speakers that actually have a non-flat response?
Well, that's kind of a pet peeve of mine. You've kind of hit the nail on the head. There's I believe that you have to have a smooth response if you're going to have a speaker that's worthy of itself and worthy to listen to. The problem with flat responses is that many of them don't take into account the power balance itself. There is where you run into the impedance problems on the low end. How do you get more power out of the low end to make it sound balanced with the mid-range and with the high end? It's the power balance skill, in my opinion, and mathematics that go into it that will define the difference there. The problem with studio monitors is really not a problem. And by the way, there are many that are vented, but these are typically tighter. They're usually a little higher resonance. Not always. They're usually in, even if they're low resonant, they're in smaller cabinets. So their responses also being made of paper are lighter, they're faster. So they're made to be quicker. You don't want the excess movement of the woofers. As mentioned in a bass reflex, they can unload, and it's that excess that can create distortion. Obviously, the tighter the spider, the higher the resonance, everything else being equal, you get a little greater sensitivity and a faster response or recovery time. So in this case, that also applies to HPass, because one of the most unique things about HPass is that the woofer, what we call the FS, or effectively the free air resonance of the driver itself, is quite high relative to where it's tuned down to. In those graphs that you showed earlier, for example, the FS of that 6.5-inch driver is 63 to 65 hertz, and yet it's tuned to 36 hertz, almost an octave below, and you saw how the response summed to be beautifully flat through that frequency range. So why the high resonance? Because you really don't want that looseness. I agree with the person that wrote in that those very low resonant drivers are somewhat sloppy, if you will. They're slow to move. They don't recover very fast, and that's distortion. If I were to explain harmonic distortion very quickly, if a woofer had to move, let's say, 1 foot to produce a certain frequency, say 40 hertz as an exaggeration, and you want it, and at the same time to produce 80 hertz, it only has to move half a foot to do the same thing. But if it's producing 80 and 40 at the same time, now you've stretched 80 out 6 inches. That's harmonic distortion. And the recovery time of that, as well as it continues to move when you get another pulse, is much slower with all that mass and having a low resonance. Consequently, there's an awful lot of distortion down there. People really, I think, don't realize may be there. Lower frequencies, we tend to put up with more of that than maybe in the mid-range and upper frequencies, which are obviously in a range where the ear's more sensitive. And in that case, we become more concerned about distortions in that range than we do the bass. So at any rate, though, I think a flat curve is a requirement. If you don't start out with something that is smooth, then how do you know if you're listening to what was recorded that has its own ups and downs?
Yeah, this has always been my argument as well. Speaking of distortion, we have one more graph to show, which is called THD, which you sent. Hopefully John can find it here. There it is.
There you go. Yeah.
And we can see that
that's a frequency response sweep, in this case at 1 watt. But what I wanted to show here was a couple of things. The red curve is the woofer itself. As you can see, the woofer by itself is pretty darn low in distortion. That red curve happens to be the one that's also in the cabinet. Now, it's effectively an overlay of the woofer itself, with the exception of right around 90 to 100 hertz, 110 hertz, where you don't even see it. It's almost even off the chart. And part of that is right where that bass trap I was talking about has some effect on that, can actually reduce some of the distortion that the woofer might have in it. In this case, there was almost none anyway. It's extremely low from 60 50, 60 hertz out all the way. But interestingly, as you go down in response, you can see that the woofer itself all the way down to 35 is still quite low, even in the cabinet. And the blue curve is the vent. Now here we have all of this compression going on inside the speaker. You could have lots of adverse effects on the woofer itself, and you certainly wouldn't think you would have extremely low distortion from the vent as well. Yet you see the vent response in that 90 to 100 hertz range is also very, very low, along with the woofer, which again an indication of what the bass trap is doing. And you can see that even the vent shows the extension way on down to about 25, 26 hertz, which is effectively where I was suggesting when we saw the previous graphs of the response of the vent. It was reaching about a minus 3 dB, minus 4 dB type point in that 28 range. Yeah, 26, 25 is about a minus 6 dB on this particular product. But these are the kinds of curves, particularly from the vent, that show a great lack of any problems with phase and obviously very low distortion content.
Now, there was one other point that I wanted to make sure we touched upon. We're almost out of time. We have a few minutes left. And that is, not only do we get greater bass extension with lower distortion from smaller drivers with H-Pass, but we also get, if I'm not mistaken, greater dynamic range. Why don't you tell us a bit about that?
Well, that's the weakest link. That was my pet peeve, and really what I was looking for 30 years ago. The fact is that if you take a bass drum, if you look at an audio encyclopedia chart of the different dynamic ranges of different instruments, actual acoustical instruments at 10 feet away, unamplified, you find things like a bass drum, timpanis, and things of that nature. Very low bass frequency type of items have a very wide dynamic range. A bass drum, about 30 to 110 to 115 dB. That's 80 to 85 dB dynamic range. Let's just call it 80 dB for a minute. Most of them in that low range will have that kind of dynamic range, low frequency range. Believe it or not, the next highest dynamic range instrument other than those in those low frequency ranges happens to be the cymbal, another percussion instrument, very interestingly. And that cymbal has a 70 dB dynamic range, from the softest you can hit it and hear it at 10 feet to the hardest you can hit it and hear it at its loudest at 10 feet. That's the dynamic range. That is loudness amplitude we're talking about now. That's very interesting, because now, even with the second highest dynamic range instrument, other than those low ones, you're talking about a 10 dB dynamic range. Well, all of a sudden, to a speaker engineer, you have two choices. 10 dB is 10 times the power, as many people know. That's why we have lots of subwoofers today. We have all of these big woofers that are insensitive, and you want this dynamic range from them, so you've got to power up, given the same sensitivity, in order to achieve the same acoustical wavefront at 10 feet to be exact with what the exact instrument will do itself. And a bass drum has a 35.7, I believe it is, 35.7 or 35.4 cycle fundamental itself, the first frequency, the first note that you hear when it's hit. And to get that out there at 10 feet at 80 dB difference, you need that 10 dB greater dynamic range, or instead of having the amplifier give you 10 times the power, you need 10 times the sensitivity from the same speaker where you need it the most, from 80 hertz down. And so in this case, H-Pass is helping supply that increased sensitivity, as I talked about a little earlier, from 80 hertz down. And that is why you get the benefit of a very even amplitude and the dynamics, which are improved and increased at typical listening distances, like your 8, 10, 12 feet.
Great. Unfortunately, we're close to running out of time. Dr. T asks, we've been talking about low frequencies all this time. What about high frequencies? And I know that you've got a ribbon tweeter which we probably don't have time to get into in any depth. So perhaps you'll come back and talk about that next time?
I'd love to do it, Scott. It's always a pleasure.
Thank you. Let's see. We'll end with this question from F-Loop. Do you have any novel technologies you're working on now, at least that you can talk about?
Well, I am, to a degree. I happen to be working on one with a tweeter, believe it or not.
Oh, well, there you go.
There you go. A little something on the other end to satisfy folks, to go along with the ribbon that I've done for quite a while as well, which is truly a planar magnetic. But yes, I am looking at a couple of new things as well. There's 3 patents out there I have now. The 4th one being this new development with HPass, and got a couple more things that you might see in the near future.
But you probably can't talk about very much at this point.
Can't talk about those too much right now. Okay,
very good. Well, thanks so much, Philip Clements, for being a guest on the show. It's been a great conversation. Certainly, low frequencies rule in my world, being a bass clef instrument player. And I thank you so much for being a guest on the show.
Scott, it's always a pleasure. Thanks for inviting me and having me on.
You bet. And we'll have you on again to talk about high frequencies next time. How about that?
Sounds great. More than delighted.
Great.
Thanks, Scott.
You can read more about Solus Clements loudspeakers, Philip Clements' company, at Solus Audio. That's SOLUSAUDIO.com. I saw an item in the chat room there. Somebody wanted to know where his website is, and there it is. My online home, of course, is hometheater.com. You can also email me with questions or suggestions for guests in the future at scott@twit.tv. And you can follow me on Twitter at htgeekscott. Next week, my guest geek is scheduled to be John Atkinson, the editor of Stereophile, who will be delivering a major address at the upcoming AES convention in New York with the intriguing title, Where Did the Negative Frequencies Go? I'm not quite sure what he means by that, but we're going to find out next week, so I sure hope you will tune in for that. Until then, geek out.